Okay, so we are going to continue to talk about relations and in particular properties of relations. But we are moving on after the sets and cardinalities of sets and onto the next topic. So several lectures ago, we talked about composition of functions. In the same way, we can talk about composition of relationships, right? So if you have a relation R going from A to B and another relation S going from B to C, then you can compose these two relations by basically using R to go from A to B and then using S to go from B to C. Okay, so it's basically like if you have so we have the set A, right? And then we have the set B, and then we have some arrows. And then we may have some C. Right, and when you compose, then what you're going to do is that basically, you go from here to here, and then there to there, and then you just say, hey, this is the, composition. And the composition includes, pretty much every element will be more or less connected to the other element. So the point is that you go from, some element here to some element there using the relation R, and then you go from some element in B to another element in C using the second relation, right? The second set of arrows. That's called composition of relations. And of course, if these arrows were actually representing a function rather than a relation, then the same, walking through these two arrows will correspond to function composition. So it's really not the case that, so function composition and relation composition are very similar, right? The only difference is function means, well, one input, there can be at least only one output. Whereas if it's a relation, the same element may be related to multiple elements, right? So we have this, in the case of functions, we have at most one outgoing arrow property, right? For relations, that's not necessary, right? So otherwise, the composition concept is basically the same. You just go in one step. For the one step, you go use R, and the other step, you use S. Okay. You can also define the notion of an inverse of a relation. You already saw an example of this in your second homework. So and you know more about this than what's being said on this slide, so I don't have to talk about that. Okay, so so the one thing you can say is that if you take a function, the inverse of a function will be a function itself if f is injective, right? Injective means that the number of incoming arrows, right? So if you take the set V, then the number of incoming arrows is less than or equal to 1, okay? Which means that when you flip this arrow, then you will have the property that less than or equal to 1 outgoing arrow, right? Which is what a function is. And so if f is injective, then f inverse will be a function. Okay. So so far we have been talking about relations as going from set A to set B. Okay. But if A and B are the same set, then things get a lot more interesting. So what we are going to do in the next few today and next on a Thursday is to talk about relations that involve just a single set, right? So these are relations that go from A to A, okay? So this means that the key property is that it can be composed with itself, right? Because it goes from A to A. So I can say R composed with R I can do, because it will go from A to A once using R and then once more using R, right? So whereas if I have two relations, right? So like this, then I can compose R with S, right? So R with S is going to take A to C, right? But now I can't do any more composition because I have, I'm ending up with elements of type C, and I don't have any relation that operates on C, right? Whereas here, because I'm going from A to A, I can keep applying the relation R again and again and again as many times as I want. And that makes it interesting. And in particular, that means I can represent them using graphs, right? So graphs are things that you are you have probably seen informally, and but we are not talking about plotting x against y. That's not the type of graph that we are talking about. We are talking about graphs as in discrete math, right? So we'll particularly start by discussing directed graph, where you have some elements, right, which we will call as vertices, okay? And we will denote them using this letter V. And then there are edges between these vertices. So we can have, for instance, we may have right? So let's say we have elements A, B, C, D, E, F, right? So so this is an example of a graph, okay? So graphs are a very important concept in computer science and combinatorics and math, and you'll see it in many courses before you're done, okay? So what we are going to do is to simply relate graphs to relations, okay? And then try to understand relations in terms of graphs, because concepts such as composition are quite intuitive in the case of graphs, right? So when I draw graphs like this, right? So you can easily see, okay, I can start from A and then I can follow edges to go to E, right? So when you look at the graph, in an instant you can tell me that there is a way to go from A to E, right? Which basically means that I can compose this relation E, right? E composed with E will have this element A comma E, because if I compose E once, I can go from A to B. If I apply E again, I can go from B to C. If I apply E again, then I can go from C to E, right? So E, if I apply this 3 times, then I have a way of going from A to E, okay? So there is sort of a natural, intuition for how we can think about paths and walks in graphs, and all of them relate to properties of relations. Okay, so again, so in a graph, right? So if you think about the way we used to represent this type of information using our, right? So this is a relation, right? So we have 6 elements, A, B, C, D, E, F. So the conventional way we used to represent this relation is, okay, A goes to B. So let's say A, B, C, D, E, F. So A goes to B, so that's one arrow. And then A goes to C, so that's another arrow, right? And B goes to C, so we have that arrow. Then D goes to C, so we have that arrow. And then C goes to E. And C goes to F. Right? So this is how we would have represented this relation using the diagrams we have been using so far. But now for a relation that goes from A to A, there is sort of a more compact and intuitive way of representing this, right? And so that's what we call as a graph. And this is called specifically a digraph because all of these arrows have a direction, okay? And then there are also graphs where there is no direction because essentially because every arrow is paired up, right? So if there's an arrow from A to B, there is also an arrow from B to A. And then instead of drawing 2 arrows in opposite in opposite directions, we just draw a line with no arrows, and that would be called just a graph. Okay, so a graph in which the edges have no directions is called I'm sorry, when you have directions on the edges, then it's called a digraph. When there are no directions, then it's called just a graph, or sometimes it's called undirected graph.
Quick question.
Yeah. Yeah.
I didn't understand the notation there where you have E, E composed, or,
Right. So E is a relation, right? Because it's just this. So this is what I have drawn here as edges is basically representing a relation over here. Okay. It is this relation that I'm representing in a different way as a graph over here.
All right.
Okay. So now if you take this relation and you ask, okay, so if I start from A and I want to end up in E, then how can I do that? So one way to do that is you apply E once, and then you start, that will get you from A to B. Okay.
Right.
Then if you apply E again, so now you're starting out at B, then you go from B to C. Okay. And then you apply E once more. So right now you are at C. So you go from C to E.
I guess my confusion comes from the fact that, A also points directly to C. And why would it go to B before going to C?
Okay. So when you compose 3 times, right? So then you have to take the arrows 3 times, right? So E itself takes you, I'm sorry, I don't know what you said. Okay, A directly goes to C, right? So in one step, you can go to C, yes, right? So
Right.
if you ask, if I compose E with itself, and so you can ask this question, right? So right? So you can ask, if I compose E with itself, which means that I'm going to traverse the arrows twice, right? Then can I, you know, go from A to E, okay? And the answer is yes, you can go from A to C in one step, and then the next step, you can go from C to E, right? So
Right.
you are right that AE belongs to the composition of E with itself, and AE also belongs to the composition of E with itself 3 times, okay?
Okay.
And that was the path I was pointing out before, right? So it's not, so each of these, when you compose E with itself, you get, you know, we can call that as E square, right? And when you compose E with itself 3 times, then we can call that, you know, E cube and so on. Each of them is a different relation. And then you're asking whether in that relation, you know, 2 elements are related by that relation or not, right? So,
okay, all right.
so we are just asking, is A E square E? Okay, so that's
yes,
one
yes.
question. And then A E cube E. That's another question.
All right,
So
thank
this
you,
is the
Professor.
question that I answered, and this is the question you are asking. Okay?
Thank you, Professor.
Okay, so that, okay, very good. So, so that's the, you know, we have this set, we have a graph G, which includes the set V and the set of edges E. So once again, we can think of, so V is called vertices or nodes, okay? And E is the set of directed edges. And we often use this kind of a pair notation, right? Ordered pair notation to say that there is an arrow going from U to V. Okay, so U is called the head of the arrow, and V is called the tail of the arrow, and an edge with the same head and tail is called a self loop. So you know, you can have a graph where you have A, B, C. There is a self loop there, and maybe you can go from here. See, that's an example graph, and this is called a self loop, right? And for the arrow, we call this as the head and tail. Maybe another way around. I should check. Okay, so let's stop here, and we'll continue in the, you know, on Thursday. And yeah, your recitation will start in 10 minutes. And again, you should really speak up. I think the class with, you know, 55 people is sometimes, you know, people don't feel comfortable speaking up, but at least make sure that you speak up in the recitations, because it's absolutely critical for us to know, you know, where you are and what you're having difficulties with, and also what's you know, easy for you, so that we can you know, tune the class and make sure that everybody's you know, that we are able to have everybody on board. Okay, so please do that. And then, you know, you know, feel free to hang up unless you have questions. If you have questions, you know, fire them away.
Oh, I was just wondering,
Yeah.
will this eventually connect to like an adjacency matrix? Because I think I learned like a similar concept like last week in my algebra class.
Right. So I'm not going to talk about adjacency, you know, matrix and so on,
Oh,
because
okay.
you'll come to that at you know, in other courses.
Mm-hmm.
Here, all I want to do is I want to sort of connect relations to graphs, and we'll stop with that.
Oh, okay. Have a good day.
Yeah, you too.
So, Professor, just to clarify back at the relations, so is that just checking when you do E A squared B, you're saying, does this relation actually exist by and the only way to find out is by going through, all the graph.
Right. So does the relation E square, will it have an edge from A to E? That's what we are asking.
Oh, okay. Yes.
Okay.
Yes.
So
I'm sorry.
and relation and E square, the edges in E square are exactly those edges which you correspond to a path of length 2 in this graph, right? In the graph of E.
And I guess I got confused on is that the modus ponens notation, where you used, you have the arrows pointing to the E and over A over E. So how would that notation work?
Which notation? I'm sorry.
So right above where you have the E circles, you have the E composed E all over.
Yeah. What is the notation you're asking?
Yes, is that?
So this is the composition notation here.
All right. No, I understand that, but the fact that you have that over, parentheses A comma E.
Okay, so I was asking, is there a way, if you take the, this composition E composed with E composed with E, in that composition, is A related to E? That was the question.
Yes. Okay. All right. Thank you. All right. Thank you, Professor.
Yeah. Okay, good. So we'll talk to you on Thursday.